So this is W1842, question paper 42. This is page 13. I think we did do this part. Hold on 1 second. So write the expression dissociation constant Ka for this. So Ka is HNO2 dissociating, and it will produce two ions, H+1 and NO2 -1. I think we did do that part, and the K expression was the concentration of the products and NO2 -1 concentration divided by the acid concentration. That was what K was. And then we also calculated the pH of this thing. Both ion concentrations would be exactly the same. So the K expression would be, it would be H+1 squared. Both of these ions would have equal concentration divided by the acid concentration, which is HNO2. And the K value was already provided somewhere, 6.9 times 10 power -4. And you were supposed to figure out the H+1 concentration. The acid concentration was also given. That's given as 0.15. So what was the answer for this one? You were getting what? I think we did this part yesterday.
Um, 1.035 times 10 to the power -4.
That was the constant, 1.035 into 10 to the power
-4.
Okay, so that's the concentration of H+1. So how do you find pH? You take the negative log of that, and you'll be able to find the pH. Hey, did you underroot this? I think you didn't.
Oh, yeah. Oh, yeah. I didn't. I need to root it. So to say.
Yeah.
10 to the power.
But if you do negative log, it's whatever you're going to get.
2.
1.02 times 10 to the power -2.
Okay, and you take the negative log, you'll get 2.
Oh yeah.
Then you have to calculate the percentage of HNO2 molecules that dissociate. So you figure out the H+1 concentration, which was 1.02 times 10 power -2, right?
Yeah.
Mole per dm cube. The HNO2 concentration was 0.15 mole per dm cube. So how much of it dissociated? So out of 0.15, 1.02 times 10 power -2 mole per dm cube have dissociated. I mean, all of these ions were produced when this thing dissociated. So calculate the percentage of molecules that dissociate. That's going to be 1.02 times 10 power -2 ions are produced per dm cube out of 0.15 mole per dm cube. And you times 100. So you'll, what do you get? What is the percentage of dissociation or ionization?
6.8.
So this comes out to be 6.8%. So is this clear? You figured out the concentration of the ions, and these ions were produced when this thing dissociated. So out of this much, these many ions are produced. As I define what is meant by the term buffer solution. So it's a solution that resists a change in pH when a small amount of acid or alkali is added to it. So when small, not large, but small amounts of acid or alkali are added. And how is a buffer solution formed? The buffer solution is formed when you mix an acid, a weak acid. Usually it's a weak acid. In this case, it's HNO2. And you mix it with its conjugate base or its salt. The conjugate base in this case would be NO2 -1 ions. So you you mix these two things, it's going to form a buffer solution. Why is it going to form a buffer solution? Because the concentration of H+1 ions would remain constant. Why would it remain constant? Because there's going to be an equilibrium that would exist between these two things. Like if you add a lot of conjugate base, which is in this case coming from NaNO2, and you've got a weak acid, which is obviously the weak acid HNO2. So what will happen is that if you, he's saying write two equations to show how the solution containing this mixture acts as a buffer. So if you add H+1 concentration, where would the equilibrium shift? The H+1 ions, the extra H+1 ions that you're adding will combine with the NO2 minus 1 to form HNO2. So that is what's going to happen when acid is added. So the H+1 combines with the NO2 minus 1 and it ends up forming HNO2. Vice versa, what's going to happen when you add an alkali? When alkali is added?
OH.
Okay, so the concentration of the H+1 ions will go down. So the equilibrium would shift forward. So what will happen is that the equilibrium is going to shift in the forward direction. And the extra OH ions will get neutralized. The H+1, the acid, will start behaving as an acid in the presence of the alkali. It will release H+1 ions. Those H+1 ions are going to neutralize the OH ions, the extra OH ions that you're adding. So when an acid is added, the conjugate base starts acting as a base. When an alkali is added, the acid starts acting as the acid and neutralizes the extra H+1 or the extra OH ions. These are your two equations. Is that?
So which one? Yeah, those equation constants.
These two.
This one.
I mean, this is basically your answer. I was just explaining this. So that's, and so then there's another thing. Why? So the other thing is why can't you have a buffer solution by just having a weak acid? A weak acid will have very few NO2 minus 1 ions. Because it ionizes very less. So it will not be able to. I mean, there wouldn't be enough conjugate base to neutralize the acid. So you need extra NO2 minus 1 ions, and those extra NO2 minus 1 ions, they come from the salt, usually from the salt. Now the next part is about. Now that is about. And let me open the notes as well. This one is probably about azodize. Okay, just a second. Okay, so we'll revise azodize. Okay, where's organic K2 part 1? And part 3. I think in part 3 we did azodize. So what were azodize? You had a diazonium ion, and that diazonium ion would go and react with activated benzenes. But over here they're saying that what's the question? Nitrous acid is used in the preparation of diazonium salts. The group in the diazonium ion can be replaced by Cl. This is not azodized, it's just the diazonium ion. The reaction can be used in the synthesis of compound Z as shown. So you've got a compound Z over here. So it suggests the reagent used in reaction 1. So reaction 1 is kind of exactly it. I mean, this is confusing because reaction 1, he's already told us that copper 1 salt, remember this is not in your course, this reaction, so they've given it. So they're saying that X could be ClBr or CN. So they've already given you the reagent. So all you had to identify was that this reaction over here that is happening, reaction number 1, is exactly the same These two are kind of exactly the same reactions. So CuX is the reagent, the copper 1 salt, where X could be Cn in this case. So over here it's going to be CuCN. So reagent for reaction 1 would be CuCN. Is that part clear?
Yes, sir.
And then he's saying that HCl is added, dilute acid is added, and reaction number 2 happens. Whenever you have a dilute acid, the CN hydrolysis happens to CN. So it will turn probably into a carboxylic acid. So you'll have CH3, and then you'll have another CH3 over here. And this thing turns into a carboxylic acid. So dilute acids, the CN turns into carboxylic acid. And then he's oxidizing it. Remember this, whenever you oxidize an arene, the carbon chains, they turn into carboxylic acid. So whenever you oxidize it, MnO4 -1, the benzene carbon chains, they get oxidized to carboxylic acid. No matter what the carbon chain is, it will eventually turn into a carboxylic acid. So suggest structures, we did that. So predict the number of peaks in the carbon-13 NMR spectra of W and Z. So he's talking about carbon-13 in W and Z. So what's W? This one is W. So W, remember resonance. The rule for resonance is, I mean, we're going to try and keep it simple. The rule for resonance is same type of environment, then they would resonate at the same frequency. So if I have this molecule, here is this carbon, and you've got another carbon over here. They both have different environments. So this one would resonate at frequency F1, this would resonate at frequency F2, because the chemical environment or the type of bonding or the electron arrangement around the atoms is different. So this one would resonate, its nucleus, its aligned and opposing spins would be a different amount of energy would be needed for that. So that's the basic idea, that different environment, you will have different resonant frequencies. So is that part clear?
Yes, sir.
So over here, how many different carbon environments do you have? Are these two carbons different or exactly the same? The one at the bottom and the one at the top.
I mean, they're the same thing.
They're the same. I mean, the environment and the structure and the bonding around them, it's exactly the same. So let's say that resonates at frequency F1, right? So then you have this carbon. Now this carbon over here on the benzene is different compared to all the other carbons in this molecule. So that would resonate at frequency F2. Then you have these two carbons. There's a carbon over here and there's a carbon over here. These two carbons are in the same exact environment. So they would resonate at the same frequency. Let's call that F3. Then you have these two carbon atoms, and they also have the same environment. So they would resonate at frequency F4. And this one has a different, I mean, they're actually, this one has a different environment. So that's frequency F5. And this one at the end has a different environment. So let's call that frequency F6. So they're basically 6 different environments. These two are in exactly the same environment. This one on the benzene is in a different environment. These two are exactly in the same environment. These two are exactly in the same environment. This one is in a different environment. And this one is also in a different environment. Is that clear?
Yes, sir.
Clear, Brar, Bazga, is that clear?
Yes, sir.
Yes, sir.
So there are going to be 6 peaks in the radio spectrum. So number of peaks, that's going to be, for W, it's going to be 6. Or the other one now. This one is, what about these carbons? Are they the same environment or different environments?
Same.
So that means let's say that's frequency F1. Okay, they're all going to resonate at frequency F1. So what about this carbon atom, this carbon atom, this carbon atom? Are they in the same environment or different? They're all
Same environment.
okay, so let's call that, okay, they would resonate at the same frequency. And then you have this one, and this one. They're also the same environment, right? So that's, they would resonate all together at the same frequency, F3. So there would be 3 environments, 3 peaks. Is that clear?
जी sir.
So ये बस याद रखना, what you should know is that carbon 13 is very simple. Okay, just remember carbon. I'll just do another one. Okay, I have this question, right? Achha, so and there's one H over here. How many different carbon peaks would you have in this one, in this molecule? I mean, there are 4 carbon.
2 3 मतलब 3 different environments.
Okay,
3 peaks.
These were exactly the same environment, right?
जी.
And this would be F3. Okay, so there would be three peaks. But the spectrum would be, okay, you'll get 3 peaks. One of the peak would be higher. The other 2 would be shorter because the absorption depends on the number of carbon atoms. So this frequency over here, F1, would be absorbed more compared to F2 and F3. Because there are more carbons resonating at that frequency. So that frequency absorption. So the height of the peak is the number of carbon 13s, or in the case of HNMR, it's the number of hydrogen protons. As anyways, moving forward, you've got this ethanoic acid turns into this one. That's an OH turning, getting replaced by Cl. That's acylation. Okay, that's what an acyl chloride is. One second. Actually, here's the. So 1 second quickly. So acyl chlorides, where did we do acyl chlorides? So acylation is simple. You just add PCl5SOCl2 to it. You can either add PCl3 plus heat, or you can have SOCl2 plus heat. In all cases, the OH gets substituted by Cl. And then the Cl is getting substituted by Cn. First one is suggest a reagent for step 2. So this is a halogenoalkane where a Cl is turning or getting replaced by Cn. This used to happen with NaCN ethanolic. SN1, SN2 reactions. So a Cl gets substituted by Cn. And then you have the Cn turning into a carboxylic acid. That is hydrolysis that happens with dilute acids. And reflux plus heat. And the last one is this ketone turns into an alcohol. That is reduction. Ketone, the last part is the ketone turning into an alcohol, a secondary alcohol. That's reduction. How does reduction happen? With a reducing agent, which in this case would be NaBH4. And that's it. NaBH4 would be the reducing agent. So those are the reactions. So remember, I just wanted to open a, and let me explain this as well. So you can just go through the notes as well. So for example, this one has a lot to do with AS actually. So halogenoalkanes, nucleophilic substitution would happen. The halogen will get displaced by OH, CN, or NH3, SN1, SN2 mechanisms. So we're doing it with CN. The Cl got displaced by CN. And then what happened? it turned into a nitrile, and then what happened? The nitrile turned into a carboxylic acid. So the CN would hydrolyze, it would decompose, water will get added, it will become a carboxylic acid. When you heat it with an acid and you reflux. So that is all that's happening in this question. And then you have this thing, you've got this thing, compound R can be used to synthesize. So what is happening here? There's an acyl chloride and there is an amine. And you're not doing anything, you're not adding any reagents. So what is happening? What's going on over here? So this is amides. Okay, where did we do amides? This is part C, right? So somewhere over here we had done distuff, and after this, there was definitely amides. So there was esterification, and this, no, not this, formation of acyl chlorides. That's, just hold on 1 second. Let me open another one. That's this one, right at the bottom of this one, we did this. Just hold on 1 second. So amides, probably before that. Just 1 second. So I can't find right now, but what's yes, this one. So take this one. I mean, this was the part. That amides or polyamides, they usually form from acyl chlorides. This one, we were trying to find this one. So they usually formed when an acyl chloride and amine, they react together. The HCl in the middle, the lone pair on N gets attracted to the carbon that's positive on the acyl chloride, and they join up, and they end up forming this amide group, and the HCl gets removed from the middle. So over here, something similar would happen because they don't have anyone else to react with. So what will happen is they're going to react with each other. I mean, that's 1, 2, 3, 4, 5. So it's not two molecules reacting together. It's a single molecule that has ended up forming an amide. So these two things are going to get together to form that amide. That's the only possibility. Either it could have been two molecules reacting with each other, that would have made sense. Or what could have made sense was that, because the number of carbon atoms are not changing. So that kind of indicates it's the same thing bonding with itself. So you're going to draw it like this. Over here, the fifth carbon, I'm going to bend it downwards. There's going to be a double bond O. And over here, there's going to be NH2. And there's going to be a Cl. Now, what will happen is that the Cl and H will be knocked out. And the N lone pair and the carbon that's positive, they're going to join up and they would form this amide link over here. Is that clear?
No, sir.
ये था ना, ये हम कह रहे थे कि acyl chlorides. Remember this, acyl chlorides and amines, they join up to form amides, right? Okay, the H and Cl, they get knocked out and they join up. You look clear enough. So what is happening here is, okay, you had, so what is
And
happening?
they just boiling it, or एक ही molecule में acyl chloride भी और amine भी, so they join up.
So they join up.
Achha.
So what I did was, I mean, this thing, and the way I figured out it's going to be a cyclic structure is, okay, it could have been, because he didn't add anything else. So it could have been two molecules reacting with each other, but it's not two molecules. The same molecule, one end reacting with the other end, because the number of carbon atoms did not change. Is that clear?
Yes, sir.
The next thing is, okay, so the H will get knocked out, the Cl will get knocked out, and they're going to join up. And then he's using LiLH4, that is reduction. Remember, amides, they get reduced. Amides, all nitrogen compounds, pretty much they get reduced. So nitrobenzene gets reduced. Amides, they get reduced. So this over here will turn into CH2 if you do reduction. So everything would be kind of the same. The N over here will be, I mean, there's no dot over here. And over here, instead of CO, you will have CH2. Okay, so the O will go away, that's reduction. And name the type of reaction, step 1 and step 2. So step 1 is...
So won't it be reduced to an alcohol?
No, this is an firstly, it's not a ketone, it's an amide. Okay, it's
all right.
So an amide gets reduced to notes. So an amide, let me just quickly get at the nitrogen compounds. I think that's azodized. So yeah. So remember this. Just a second. तो वैसे बता देता हूँ कि an amide, whenever you have an amide, okay, remember it's not a ketone. Whenever you have this thing, so this thing turns into a CH2 group. That's it. Okay, is that clear? So step 2 is reduction, and step number 1 was condensation or elimination. And compound R can be polymerized. Draw a section of the polymer showing to repeat units. What is R? It can be polymerized, so it can definitely be polymerized because now we're going to do the same thing, but it's going to be with other molecules. So that's 1, 2, 3, 4, 5 carbon atoms, right? So you've got 1, 2, 3, 4, and 5, right? And you had an NH2 on this side. And you had an acyl chloride on this side, right? Now there's going to be another molecule, 1, 2, 3, 4, 5. There's going to be another molecule, and it's going to have double bond OCl, and it's the same exact molecule. But now it's going to form a polymer. It's going to do the same thing, but with another molecule. So the Cl and H will get knocked out, and they would end up forming an amide link between them. And this thing will also happen on the sides, on the edges over here with other molecules. Just going to repeat this thing. This process would endlessly get repeated. So it will endlessly get repeated. So this is what's going on. Whenever you have a double bond O and Cl, N and an H2 on one side, and you have another molecule which has exactly the same thing, or it could be the same molecule. The Cl and H, they get knocked out and amide bonds are formed between them. And the thing would repeat over here again. This thing would repeat over here again. So they would get polymerized. And that's, they're asking you to draw the repeat unit. So the repeat unit is this one. And you write N. That is going to repeat over and over again. Is that clear? Clear here?
G section.
So the next thing is again about polymerization. So they have, I think they have an amide link over here. Now he's saying, so now what they're saying is it's can be made by the reaction of this thing with a diol. R1 and R2 are hydrocarbons, so there's some sort of carbon groups. And he's saying Lycra is a polyurethane formed from this and this. So this is Lycra, right? And he's saying Lycra is a polyurethane. So basically these two are the same things. And he's saying that, so he has said that this is Lycra, right? No, he's not saying, that's not Lycra, that is P actually. So he's saying that P and this molecule over here, so this is what they mean. They gave us an example reaction. So this molecule over here is this molecule. The diisocyanate P, it's this one. They've given that as P, so that's this one. And this molecule over here is this one. And you now have to figure out what Lycra is. I think he has said that draw the repeat units of Lycra. So all you have to do now is, over there they're using R. So you have to figure out what R is. So if you look carefully, you can try matching this. So all you have to figure out is what R is. You have O double bond C double bond N, right? So that's this part. I'm underlining this. So that's this part. So that's similar. And then you have R1. So what is R1? R1 is, I think, this entire thing is R1. Right? If you look carefully, after R1 there is N. So it's N, R1, then N. So it's N. This entire thing is R1 and then N. And then there is C double bond O back again. So this thing, and then this thing over here, the diol is this one. So R2, what is R2? You've got OH on both sides, you've got OH on both sides. So R2 is probably this thing over here. So you have to now figure out what Lycra is. So you figured out what R1 and what R2 is. So what is Lycra? You just draw this molecule and you just substitute what R1 and R2 is. Is the question clear?
Yes, sir.
Ibra, is this clear? Remember, it's got nothing with what you study, it's just common sense. This reaction, you did not do this reaction. So you just had to compare this. And the first part was, the second part was draw the repeat unit of Lycra. So we'll just copy this thing as it is. There's a continuation bond, there's C double bond O, then there is NH, and then you have R1. So I'm just going to write the molecular formula of R1. I'll just write benzene is C6H4. Then I have CH2. Then I have the other benzene, which is again C6H4 in this case. And so that's R1. Then start repeating after that. Then there is NH. And then there is C double bond O, right? And after that, you have a single O. That's an ester link. Then you have R2. What is R2? R2 is two CH2 groups. And followed by a single O. So that is what Lycra is. So is this clear, this question?
Yes, sir.
And the next one is fibers of Lycra are strong due to intermolecular forces between polymer chains. Complete the table to identify two intermolecular forces responsible for this. So you're saying that it's strong. So what are the two intermolecular forces? First thing, when you have NH, that is going to lead to what type of intermolecular force? Okay, it's going to be hydrogen bonds, right?
Mm.
And the other one is what other force do you have?
Van der Waals forces or dipole.
Okay, so you do have, I mean, you've got this bunch which is non-polar. So you've got Van der Waals force. You've got all types of forces actually. Even the serial bond O is polar. So you've got permanent dipoles as well. I mean, Van der Waals forces are always present. So you've got permanent dipoles as well. But the strongest one is definitely the hydrogen bond. So the benzene rings would be producing, the R group would be producing Van der Waals forces. So they're also asking about the groups involved. So for the groups, you're going to write for this one, hydrogen bonds, it's NH. For Van der Waals, it's the R group. And if you're writing about serial bond O, then you're going to write that it's going to form permanent dipoles. I said, name one example of each of the following types of polymers. So a polyamide, you've got, I mean, this is O-level stuff. It's nylon, it's Kevlar. Okay. So polyester synthetic, what is polyester?
Oh, tellurine.
Yeah. And then you have a conducting polymer. And I said the last two, let me just check about the last two, whether it's still in your syllabus or not. Because I think it got removed. I mean, the conducting polymers are there. One second. So predict the type of polymerization, monomer or peromonomers, identify the degradable polymers. That's fine. It's so glues. I said definitely glues are gone. It's no longer there, so you don't have to. Let me just search epoxy. Still zero result. That thing is gone. So glues are gone. Conducting. Polymers. We do not see anything about conduction.
Mm.
Just it's a pretty basic polymerization. I mean, it's just basic O-levels polymerization now. So that is, it's just mostly O-levels polymerization now. So that thing is now gone. So we can leave that part for now. So you had, but I'm going to tell you what a conducting polymer is, by the way. A conducting polymer is one that has alternating double bonds. Like if you have a polymer chain and you have alternating double bonds, it's going to conduct electricity. Why? Because the double bonds, the pi bonds, they were overlapping over here and they were overlapping over here. But when you have alternating double bonds, just like in the benzene ring, the double bonds would become delocalized. So alkynes would form conducting polymers, but let's leave that now because it's no longer in the course. And the glues as well. So the next part is what is meant by the term free radical. A free radical is any species that has unpaired electrons. So that's the answer to that. Suggest an equation for a possible termination step in this process. The equation in this process, a possible termination step, any two radicals can join up. If you remember, like if you have NHCl, that's a radical, right? So a possible termination step, that's a radical. And you can have another one. Just one second. What's the question? They form two radicals, right? Then this radical goes and attacks the other one. So suggest an equation for a possible termination step. I mean, you can combine with another Cl radical and end up forming NHCl2. Its bonds would be complete. So any atom whose bonds are not complete is a radical. So the two would join up, and what else can happen? Two NH2s can get together. That could be a termination step as well. Like N has incomplete bond. There's another NH2. It's got incomplete bonds. They can sort of join up to form N2H4. That's AS termination. If you remember that any two radicals can simply join up. You're being asked to draw the Doran cross diagram. So N has 5 electrons, 2 H's, and 1 Cl. So you got 1 Cl. There's an N in the middle, and there are 2. He's saying state the type of hybridization of the nitrogen atom bond angle in the NH2Cl. Now remember this, if the rule is, especially for oxygen, nitrogen, and carbon, the rule is if no pi bonds, that is sp3. All single bonds, that's sp3. If one pi bond, like one double bond, that's sp2. And if you have 2 pi bonds, that would make it sp. So for carbon's case, it was, the first one was CH4, but the same rule applies to N and oxygen as well, because they have almost the same electronic configuration, except that they have lone pairs. So in this molecule over here, all are single bonds. So it's going to be sp3. Okay, so they're all single bonds, 2 H's, 1 Cl. On the top, there's a lone pair. So it doesn't make a difference. The shape of the bonds are going to be exactly the same. The CH4 and the NH2Cl would kind of be the same thing. The fourth side is not making a bond. The reason it's not making a bond is because its orbital is already full. So remember this rule, no pi bonds. If they're not making any pi bonds, that's sp3. 1 pi bond, it's going to be sp2. 2 pi bonds, it's going to be sp. And the bond angle in this case would be, that's molecular geometry, that's going to be 107. It should have been 109.5, but the lone pair causes more repulsion. So it's going to be 107 degrees. Is that clear?
Yes, sir.
Yes, sir.
And this is about entropy. Define the term entropy. It's disorder. It literally means disorder, or a measure of the disorder, sorry. And you've got calculate the standard entropy delta S for this reaction. So how do you calculate entropy? What's the formula for entropy? It's Delta is the entropy of the products minus the entropy of the.
minus that.
So you can, the entropies are given. So all you have to do, and I mean, multiply by moles, it's 1 everywhere. So it's going to be the entropies of the product. So I'll just write the expression, which is the entropy of HCl. What's HCl? It's 187. And the entropy of the other one, N2H4, that's 237, right? So that's my product minus my reactant, and my reactant in this case is NH
241.
241, and the other one is 198. So you'll find the entropy change and calculate the standard enthalpy change. How do you calculate the enthalpy change based on the enthalpy of formations? So if you're given the enthalpy of formation of the products and the enthalpy of formation of the reactants, then it's kind of the same formula. Actually, it's products minus reactants. The enthalpy change would be the enthalpy of formation of the products minus the enthalpy of formation of the reactants, which would be 95.4 minus 92.3, that's my products, minus my reactants, the first two, that's 80.1, and minus 45.9. Make sure you be careful with the signs. You've got products, one of them had a negative value. So now you're saying calculate the standard Gibbs free energy of this reaction. So for the first two, what values do you get for this one and this one? For Gibbs free energy, you need both. Gibbs free energy is delta G is equal to delta H minus T delta S. And for that, you need delta H. So the first one is going to be, what is 187 plus 237? Minus this, this would be 8. And I think it should come out to be
minus 15.
Are you getting minus 15? Okay.
Yeah.
And what about this one? It's going to be
minus 31.1. Yeah.
So, and remember the units. Enthalpy is always calculated in kilojoules. Entropy is calculated in joules. So be careful about the units. So you have to convert the units into delta. Gibbs free energy is usually in kilojoules. So you would have to divide this by 1,000. So it's going to be delta H is minus 31.1 minus 298 and multiplied by delta S, which is going to be minus 15 divided by 1,000. So make sure you divide that by 1,000 and you'll get your answer. So let's continue with the same thing tomorrow then. Okay.
Part 5 why this reaction becomes
for that I would need delta G first. What's delta G coming out to be? It's okay, you don't actually need delta G. Explain the reference to delta G where this reaction becomes less feasible. Now delta G is the overall energy available to a system. If it's exo, right? If it's negative, that means the system releases energy and that's a feasible reaction. It doesn't need energy. So for feasibility, this should be negative, right? Is that clear?
Yes, sir.
So what is given is that you already know what enthalpy change is. It's negative, right? I mean, it's given, you've calculated that came out to be negative. You also know entropy change, that's also negative. So this is also negative. So a negative thing minus T times negative thing, that would become a positive thing, right? Is that clear?
Yeah.
So one of the part is endo, the other part is exo. Now, for a feasible reaction, we want to make the overall thing exothermic, right? So we want to make it exothermic. So we're going to try and keep endo as small as possible. Then the reaction will be feasible, right? So T should be small if delta G is to come out to be negative, right? I mean, how can you make it small? You're going to make T small. then this part would become small. Is that clear?
जी sir.
So he's saying, okay, what will happen to the, so it would be feasible. I said it's going to be feasible if T is kept as small as possible. But he's talking about higher temperatures. So at higher temperatures, what will happen? ये वाला part, this part over here is going to become big. So instead of being negative, it would come out to be endothermic. It's going to come out to be positive. It's going to be not feasible. Is that clear?
जी sir.
So it's going to be less feasible at higher temperatures. I'm going to explain that if you increase T, then minus T delta S becomes more endothermic, and delta G becomes overall endothermic, or becomes positive. So कल continue करते हैं, ठीक है? Let's continue tomorrow. Okay.
Sir,
Okay sir. Last.
हाँ जी.
sir, what about my confusions that I've sent you?
Nee, which one? Sorry, I couldn't hear you.
The confusions of past papers that I've sent you a few days ago.
Can you send? Can you just write any letter and resend that? I mean, the messages, they just disappear at the bottom somewhere. So can you just type any letter and just send that? Just message me.
I just did.
Okay. Okay.
Thank you.
Okay. Take care.
Okay.